Okay, recording has started, and microphone's turned on, and let me have you start with a practice quiz, and I'm going to have you do, we're going to jump right to number 4, because this is something that we didn't have time to finish last time in class, so I'm putting it in the practice quiz. So, inverse tangent of x is related to this triangle somehow. And place inverse tangent of x in the right spot. Does it belong here, 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 or over here? Is it one of the sides or one of the angles? You determine that. I'll give you a minute for that. Alright, so on this one, we had talked about last time that when you take the tangent or any trig function of an angle, you get a number. But when you take the inverse tangent of a number, you get an angle. So the inverse tangent, theta, this is an angle. It's the angle who, when you take its tangent, you get x. Now, in other words, we could, let me change color, take the tangent of both sides. And when we take the tangent of theta, we get the tangent of the inverse tangent of x. These two cancel each other out. And it's the same as tangent of theta equals x over 1. Now, that's exactly what you would find out if you took the tangent as opposite over adjacent x over 1. Okay. But this right here is not only theta, but it's also the inverse tangent of x. Alright, so now when you have more complex problems to do, for instance like this one down here, you're going to have to construct the right triangle such that this inner portion is your angle, and you have to then label the sides such that when you take the opposite over the adjacent, you get this thing x, which is the same as x over 1. Okay, now it could be anything that has the ratio of x. So it could be like 3x over 3 or 5x over 5. But the simplest is just x over 1. Alright, now the next question is label the hypotenuse of the above right triangle. So this hypotenuse from here to here, the longest side, find out what it is if this is 1 and this is x. And then use that right triangle with all three sides labeled to find the cosine of the inverse cotangent, or the inverse tangent of x. So let me give you a minute to finish these 5 and 6. Alright, so I'm going to, the hypotenuse, let's call it W for a minute. W squared from the Pythagorean theorem is equal to 1 squared, oops, I got, how did that happen? Alright, so let me, 1 squared plus x squared. So then we got to solve this thing for w. So w is equal to the square root of 1 plus x squared. Alright, so then we've labeled the hypotenuse. So then we use that triangle to figure out what the cosine of that angle theta is. So we go back and forth. Sometimes we think of it as theta, sometimes we think of it as the inverse tangent of x. That's the same thing. So the cosine of that theta is simply the SOHCAHTOA, adjacent over the hypotenuse. So this is equal to adjacent over the hypotenuse, and the adjacent is 1, and the hypotenuse we just figured out, square root of 1 plus x squared. Alright, what we find out in this practice quiz problem, which was similar to a few of the problems, I think it was like 84 through 87 in the homework, was that when you take a forward trig function, if you take a forward trig function of an inverse trig function and they're the same, well, we know that these will cancel out and you won't have any trig functions. But when you take a forward trig function of any inverse trig function, if they combine like this, you'll always get no trig functions in your result. You'll get what's called an algebraic function. It won't be exactly a cancellation, but you won't have any trig functions in there because this is an angle and you can kind of work it out by once you fill in the sides of that right triangle. Alright, so give me a little feedback on this in the chat portion. If everybody could just tell me how they feel about that one. You got it? Doesn't really make sense. That's good. Alright, need more practice. Good, good. Alright, let me go back and just review it right now. The homework problems will be like this. Find, and this is actually one of the homework problems, find the cosine of the inverse tangent of x by using a right triangle. And so if we had to start with this one right here, how would we proceed? We would proceed by, first of all, with one right triangle. All those two trig functions, you only draw one right triangle for it. This is an angle. That's a big thing to realize. This thing goes right here. It's the angle. When you take its tangent, you get x. So we tend to call that theta. But the tangent of that theta is going to be opposite, SOHCAHTOA, opposite, over adjacent. So turn this x into a fraction, x over 1. Put the x here and the 1 there. That's the picture that we make from has. And then we're going to be taking the cosine of that angle. And the cosine is the adjacent over the hypotenuse. But we'd have to figure out the hypotenuse by the Pythagorean theorem. You'll get more practice with when you come back to those problems in the 80s on that. But I can also put this in a future practice quiz to make sure that we reinforce this.
Professor?
Yes.
So is that the same thing when you have sine as well? So the inverse sine of x?
If the original problem had inverse sine, or let's say sine instead of inverse, instead of cosine, or yes.
It has cosine times the inverse sine of x.
Yes.
So you would just take sine of x, the inverse sine of x, and make it into a fraction, which is x over 1. Same thing with you
Yes.
did, like tangent. And then you would just figure out what cosine is.
That's correct. So if it was this, the cosine of the inverse sine, instead of saying cosine times the inverse sine, we'd have to be careful to say cosine of the inverse, because this is a function and that's a function. Cosine of the inverse sine of x. The inverse sine of x is the angle, and it goes right here. It's the angle that when you take its sine, you get x over 1. Now, sine is opposite over hypotenuse. So it would go like this time. X over 1. The 1 being the hypotenuse, the x being, because sine is so opposite over hypotenuse. And then we'd have to figure out what this one was by the Pythagorean theorem. And then once you figure out what goes here, it would be that thing that you put here divided by that, because cosine is adjacent over hypotenuse. Does that answer?
Oh, okay. Yeah, that makes sense.
Okay.
So it's basically asking what is the cosine of the given angles or given sides that it already has, right?
Mm-hmm. That is right. It's kind of a strange construction when you have a inverse trig function of a trig function, and when they interact like that. But they'll always interact to cancel each other out. Sometimes directly, but at least indirectly with some kind of triangle that you can draw. Okay. And all right. Now today's lesson, I am going to. Today we're going to get into new stuff. From now on, everything will be new, related to calculus, not to algebra. We're not going to be reviewing algebra stuff. We'll be digging into new material. And so I'm going to invert the order in which we do things. I just wanted to go over this one problem to clarify something that we had, not had time to finish up in the last lecture. But I want to go right to 2.1 to make sure that you have ample time for the ideas in 2.1 today. And then at the end today, we'll come back to the other parts of the practice quiz. All right. So 2.1, the idea of limits. And brief overview. On the very first day that we had class, remember when I was telling you, what is calculus all about? Well, there was a problem that Isaac Newton was trying to solve, and that was why the planet's motion is the way that it was. And in order to do that, he had to come up with a new type of math. And this new type of math had to do with finding things. Now, this wasn't the type of problem that he had, but it's a simpler type of problem that we could understand easier. And it's similar to the kind of new math that he had to come up with, but in a different context. So This is a situation where you imagine that you're driving your car from your house. And the time that you've driven, so you've driven a total of 3 hours, and you're going to eventually get 150 miles away from your house. So if we look at this situation, and what I want you to do right now is get into your text groups and tell me, in this situation between 1 hour and 3 hours, if this is the time and this is the distance, when were you driving the fastest? Give me an approximation of when this driver is driving fastest. And I'm going to give you just a quick, 30 or 40 seconds, and then I'll ask a group or two. When is this person driving fastest? All right, let me ask group 3. When is it going the fastest?
I'd say around between 1 and 2 hours.
Okay, and how did you decide that it was there between 1 and 2 hours?
Because of the steepness of the curve of the line.
That is correct. How fast you're going has to do with it all has to do with the steepness of the curve. And there's one point in particular where you're going faster than any other point. Maybe that point's here. And then what we call the tangent line to the curve. The line that just nicks the curve there. Now, I didn't draw that tangent line very good. Let me do that a little bit better. The line that just nicks the curve there. The slope of that line would be how fast we're going when we're going the fastest. And it was, I can imagine, a huge debate at the time. That if somebody said, yeah, we can find the exact slope at a particular point, which is called the instantaneous slope. In fact, we could find the instantaneous slope at any point. Suppose we wanted to find the exact speed at t equals 2. Then at t equals 2, we'd find the exact slope of this line. The line that just nicks the curve, that's tangent, what we call tangent to the curve right there. Now, the debate might have been a really hot debate, because somebody else would have replied, oh my gosh, 1/1,000,000th of a second later, it's going to be a different speed. So there's no way you're going to ever be able to find the exact speed at exactly t equals 2. And even 1/1000th of a second later, it's a different speed. It's just, there's no way you could get, it's constantly changing. The slope, the instantaneous slope is constantly changing as you're moving along here, and there's no way we could ever get these instantaneous slopes. And what Isaac Newton had to do was to create a whole new type of math so that he could get these instantaneous slopes. And that's what we're going to be heading towards in today's lesson, the idea of limits. He had to create a whole new concept called a limit. He and Leibniz both did this. And this idea of limits lets them eventually get these instantaneous slopes. All right, so we're going to start with specific problems. And problem number 1, IBM stock at year 3 was $40 a share. At year 7, it was $120 per share. Now, number 2 says, suppose all the growth occurred in the first year, between years 3 and 4, and then from year 4 until year 7, the price per share stayed at $120. All right. It asks you to illustrate with the graph, so you're going to have to draw a picture of what's going on, and then answer this question: what was the average rate of change? On average, how much did the price per share increase each year? And so, what I want you to do now is independently draw a graph to illustrate this situation, and then come up with your own estimate for the average rate of change. And then go into your group and then compare answers, and then I'm going to poll a group or two to see what kind of answers you got. So I'll give you a couple minutes on this. Okay, about 30 seconds more. All right, let me ask group 5. On average, how much did the price per share change each year?
It changed by $80 a year.
$80 per year.
Mhm.
Okay, and how did you get the $80?
We got it because at year 3, the price is $40, and then at year 4, it goes up to 120, and then it stays there. So there was a growth of $80 from year 3 to year 4.
Ah, okay. From year 3 to year 4, the slope of this was 80, so it's going up $80 per year. And then from here to here, it stayed steady. All right. Now, if we were just going from year 3 to year 4, your answer is correct. And it would be going up $80 per year. If instead, and I could have been clearer with the question, I really wanted it to go from 3 to 7. These are the only really important numbers. In year 3, it was $40 per share. In year 7, it was $120 per share. So if that's the case, then let me clarify this then. Then we're looking at what's the average increase per year.
Oh, I understand.
Would it be 25?
What's the slope?
What's
the slope of that line?
I said 20.
And so now this point is 340. This point is 120. So the slope, let's go back to red, the slope is the difference in the y's over the difference in the x's. 80 over 4, which is 20. All right, so what it's saying then, what's the average rate of change per year would be 20, and then the units would be dollars. It's always the units of the vertical axis over the units of the horizontal axis. Dollars per year. So in the 4 years, from year 3 to year 7, if it went up $20 per year, it would have covered those $80 in growth, like this. All right, so that would be the formal answer that we would get over here. I totally understand your answer of 80. And I could have been more clear on this. What's the average rate of change from year 3 to year 7, not from year 3 to year 4? Okay. Now, number 3. Suppose all the growth occurred in the last year, just between year 6 and 7. From year 3 to year 6, the price stayed at 40. Then what's the average rate of change? And you need to illustrate with a graph. So you need to draw a picture of this and find the average rate of change. So again, do the same thing. Work on your own. Check in with your group. And I'll call on a group in a minute. Okay, so let me ask group 4, what'd you get for this one?
Would it just be the same way you did it for the last one? So would it be like 120 minus 4? And then 6 minus 3?
Okay, and then what's the final answer that you got?
80 over 3?
Um,
Or, I don't know, I was a bit confused on this, to be honest.
okay, so explain to me how you're getting your answers again. Slow down.
So I tried to reason that, like,
Mhm.
at year 7, it went up to 120 from the $40 it was worth at year 6.
Okay,
And, or should I have started at year 3 with that 40?
7, 120, and 3, it's 40. Okay, and so
And then you would just find a slope for that, I guess.
um, should we wind up finding this slope again from here to here? Or should we find the slope from here to here? Which slope should we find? The red one or the black one?
Maybe from the year 6.
From the year 6 to the year 7? Okay. If we did that, it would take 1 year and we would go up $80. Okay? But if we're again emphasizing this, that, you see, the one thing that's constant in both problems is in year 3, it was $40 a share. In year 7, it was $120 per share. But in one situation, almost all the increase happened at the beginning. In the other situation, almost all the increase happened at the end. But in either case, we started here, we ended here. Year 3 it was 40, year 7 is 120. And so the average rate of change from the beginning to the end will only take these 2 points into consideration. So once again, we'll do M. We'll do the exact same thing. 120 minus 40 over 7 minus 3. 80 over 4, which is 20. We're going to get the slope, in both cases, we get the slope being 20 from the initial price to the final price from year 3 to year 7. All right. Now, what this situation is telling us, though, is that, and we call this the average rate of change. The average rate of change doesn't care how you got there. It just cares what your initial point was and what your final point was. If your growth happened this way or this way, it has no effect on the average rate of change from the first point to the last point. We could have had even stranger situations where IBM stock went up to $200 a share and then went back down to $120 a share. And your average rate of change from year 3 to year 7 would still be $20 per year. We don't care how you got there. We just care what the beginning point was and what the end point was when we're talking about average rate of change. All right, so now number 4. From 2 points, and let's put this down. Suppose I have one point being here, which its coordinates are x1, y1, and a second point here, and its coordinates are x2, y2. Then write an expression for the average rate of change if you are moving from this point to this point. So if you're going from there to there, write that expression. So let me give you all a moment, and then you can discuss it in your group, and I'll call on a group in a moment for number 4. All right, group 2, do you have an answer for that? What's the expression for the average rate of change?
It's y squared minus y1 over x squared minus x1.
All right, so we get this line from here to here, and the average rate of change is, we're going to call that, another word for average rate of change is slope. So it makes sense to use the letter M for slope. And your expression again, you said, was what?
Y squared minus y1 over x squared minus x1.
Okay. And when the subscript is on the bottom, instead of calling it squared, we'll just say y sub 2
Oh,
minus
okay.
y sub 1. We'll just put the word sub in there instead of, and then x2
Okay.
minus x. And sometimes we skip the sub and we just say x2 minus x1. Okay.
Okay.
So, and now, visually speaking, it was this. You see, let's look at these two graphs together. This point right up here, it was 3 over and 40 up. This point corresponding to it over here is x1 over and y1 up. This point is x2 over and y2 in its height. And when you take the difference in the y coordinates, y sub 2 minus y sub 1, it just tells you this distance from here to here. And that's the rise. And when you take x2 minus x1, it just tells you this distance from here to here. That's the run. So it's just giving you the rise over the run, which is the slope. The average rate of change is another way of saying slope. And remember the point that we learned in this first 2 problems, first 3, was that it only depends on the endpoints. How you got there doesn't make any difference for average rate of change. All right, let's go to number 5. On a circle, a tangent line at a point just nicks the circle, touching it at only one point. Let me draw a quick picture of this. If I have a circle, a tangent line to the circle, just nicks the circle at one point. All right, now the tangent line on a circle also represents something. Does anybody ever remember doing something like this? You could take a string and take the end of the string and tie a rock onto the end of the string. And then you start whirling that rock around by making small circular motions with your hand, and that rock goes round and around and around. Now, that path of the rock would be the circle right here. The tangent line is actually the instantaneous direction that the rock is traveling in. How do we know that the rock is really traveling in that direction? Well, suppose the circle, suppose the rock escapes from the knot, then it's going to fly, it's going to keep going in that direction. The only thing that kept it in the circle was that the string constantly pulling it back towards the center of the circle. So if it escapes at any point, you see its instantaneous direction was along that line. All right. Now, while a tangent... okay, so let me start over again. On a circle, the tangent line and a point just nicks the circle, touching only one point. On a general curve, the tangent line nicks the curve, may eventually touch the curve elsewhere. We can see that with something like this. If I had a curve that looked like this, and I had a tangent line here, this tangent line just nicks the curve right here. But it can also smack the curve way down here. So, the general curve, a tangent line may touch elsewhere. While a tangent line focuses on one point on a curve, a secant line needs 2 points on a curve. And a secant line is simply the line between the 2 points. Now, in your graphs above, when you connect the 2 given points with a line, so over here we connected 3, 7, and then over here, these same 2 points, these same 2 points. When you connect the 2 given points with a line, is this a tangent line or is it a secant line? And what does its slope represent? So, discuss that in your groups, and I'm going to call on a group in a minute. Okay, group 6. What is this a tangent line or a secant line?
For the ones above, they're going to be secant lines because they're touching 2 points.
Okay, and what does the slope represent?
Well, the slope in those the slope of the secant line, I guess, would represent the slope of those 2 points.
That is correct. And you could also say that the slope represents what? Now, when we say represent, we kind of mean like, what does it mean in terms of stock prices?
The average rate of change.
It's average rate of change. That's right. All right. So we have secant line. And this is, once again, the average rate of change. And average rate of change is a really big deal for us. It's the essence of the relationship between the 2 variables. Like, for instance, if I bought this stock in year 3 at $40 a share. In year 7, I sold it $120 per share. I'd be very interested, you know, how much was it going up per year? Oh, it was going up $20 per year on average. All right? I'm really interested in that. Now, there are other times that instead of looking at the average rate of change, I want the instantaneous rate of change. Instantaneous rate of change is going to be not a secant line, but a tangent line. It's going to just nick a curve. Okay. But so far, all our examples have been on secant lines. All right. Now we go to a new set of problems. A tank holds 1,000 gallons of water, which drains from the bottom of the tank in half an hour. The values in the table show the volume V of water remaining in the tank in gallons after t minutes. So this tank, at time 0, there's 1,000 gallons. After 5 minutes, there's around 700 gallons. After 10 minutes, there's around 444 gallons, and so on. By the time of 30 minutes, all the water is gone. All right. First question, number 2. When is water emptying the fastest and why? Discuss that briefly in your groups. I'm going to ask a group in a minute. All right, group 5. When is the water emptying the fastest?
Between minutes 0 and 5.
So right at the very beginning. And why is it emptying fastest at the beginning?
I don't know, about half the water-ish. Like at least 300 gallons have gone out of the tank by the time that 5 minutes has passed. That's the most of any other 5-minute sector.
Very good. Any other 5-minute sector is by far the most, and if we compare it like to the last 5-minute sector, only 28 gallons went out. 300 went out over here. And it seems to get smaller and smaller, the amount that goes in each 5-minute gap. And is there a physical property in terms of physics that would kind of tend to tell us why? Anybody want to interject with that?
It'd be the largest mass of
Water pressure.
Yeah, water pressure.
and the force of gravity operating on a larger mass.
Force of gravity with lots of pressure above it.
And the mass goes diminishing as it goes.
As it goes down. Okay,
right.
So we're going to see it gushing out of the tank at the beginning. And actually, when is water emptying the fastest? We might even say t equals 0. And then a moment later, it's going to be slowing down and slowing down and slowing down. Okay. Now, number 3. Estimate how fast the water is leaving the tank at t equals 15. Now this one you really have to think about. So I'm going to give you a couple minutes to really ponder that and then discuss that in your group, and I'll call on a group in a couple minutes. All right, let me have you stop. Group 4, you have an estimate.
Could you choose a points like 0 and 1,000 and 5 and or wait, hold on. Like could you choose at 0 minutes and 1,000 gallons and then at 15 minutes and 250 gallons and find the slope for that?
You certainly
'Cause
could.
okay.
Okay? And so if you did that, let's look at that. So you took the point 0, 1,000, and the point 15, 250, and then we'll find the slope. M equals 1,000 minus 250 is going to be 750. And then 15 minus 0 is going to be 15. And then that's going to be
50?
50?
Yeah.
And what would the units on that be? 50
Gallons over units? Or I mean over minutes?
gallons per minute. Okay?
Yeah.
Now, what that represents is the average. Remember back up here, these were average rates of change. This is the average rate of change from 0 to 15 right here. And it's 50 gallons per minute. And that could be an estimate for how fast the water is leaving the tank at t equals 15. Now, did anybody do it a different way?
I tried to get as close to the interval that at 15 and 200, so 15 minutes, 250 gallons. So I took the slope between the 10 to 15 interval and 15 to 20 interval, and I kind of tried to find a medium between them.
All right. Well,
I did it differently.
And what did you do?
I just took 250 divided by 15, which gives you how many gallons per minute.
Okay. All right. Now, let's look at that last one, that last suggestion. If you took 250 divided by the 15, what does that give you?
That gives you 16.66 gallons per minute. Lost.
16.67. All right. So that would have the right units of gallons per minute. But this is not kind of like, what we're really looking for is how fast is it emptying. What this gives us is something like at this snapshot in time, there's 215 gallons after 15 minutes. This would be really important to us in a slightly different situation. If we were, let's say, filling up the tank with water, and we were starting with a tank that was empty, and we were putting in the same amount of water. We turned on the hose at a constant rate, and we were putting it in for 15 minutes, then the 16.67 would represent how many gallons of water per minute has been going into the tank. And that's really important for us to understand, so I'm really glad you put that in. This doesn't get us this answer about how fast it's emptying at 15 minutes, but it gives us kind of a context of kind of understanding, like, and that's a really intuitive thing to do, to want to take these two numbers and just divide them, because it'll give us a number that will be a meaningful number, but actually in a different situation. Does that make sense?
Yeah, that makes sense.
All right. So then, if we're seeing how fast it's emptying, we need to take differences. How much water left over certain time periods. One time period that was suggested was from the beginning all the way to 15. The second time period that's suggested was just from 10 to 15. Now if we do this from 10 to 15, let me go and do this one, and I'll do this in blue. We'll take from these 2 points, 10, 444 to 15, 250. And then the slope is the difference over the difference. And then what does this turn out to be? This turns out to be
It's negative 38.8,
all right, this turns out
which
to be
is
negative
194 over 5.
All right, now this one turned out to be negative. Oh, look at, because I took a shortcut on this previous one, 250 minus 1,000 should have been negative. Because I didn't write out, here I wrote it all out. I should have done that on this previous one. And this is the rate that water is leaving the tank. That was negative 50. All right, now, we get 2 legitimate answers for this. Going from 0 to 15 or going from 10 to 15 are both reasonable ways to say how fast the water is emptying at t equals 15. But which number is better? Anybody want to chime in on which of these numbers is better and why?
Definitely the negative 38.8.
I didn't understand it. Say that again.
I would say the negative 38.8 because that slope is more representative of that instance in time.
It's a closer interval. What we're seeing is, you see, if we did the slope between just the first 2 points, it would be what? About 300 gallons disappeared in 5 minutes. 300 divided by 5 is about 60. Yeah, I think 60. 60 gallons per minute was going out way early. But when you get down closer, it's only 38.8 gallons per minute is happening from here to here. And so that is correct. As we get closer and closer to this time of 15 minutes, we're going to get more and more accuracy as how fast the water's leaving the tank then. The further away we are from it, the more we're being influenced by, there was so much pressure at the beginning, but there's much less pressure on top of the water over in this time interval. All right, so we'll trust this answer better than this answer. Is there anybody else who did it yet different than that? Because these are not the only 2 ways to do this. There's another equally valid interpretation. Anybody else come up with a different answer?
No, I didn't do it this way, but I was considering some way of reducing the interval instead of like with the last example here, we took from 10 to 15 minutes and use those 2 as 2 points. But what if you could have some method where we had 15 and then something very close to 15 as the other point? Then we get a really close
That's
estimate
right.
of what the
If
slope
we
was.
had the data by 1s instead of by 5s in minutes, we'd get even better estimates. But suppose this is all that we have. We only have it in 5-minute increments. There's still another way that we can get this.
Well, a young lady in our group she did first figured it from 10 to 15, and then also from 15 to 20.
Very good.
And then average those 2.
Very good. Let's look at that. So the other way to look at it is, because if we're just doing from 10 to 15 minutes, we have a problem here. Is that we're only emphasizing the 5 minutes before 15 minutes. The 5 minutes after 15 minutes is just as important as the 5 minutes before the 15-minute marker. We shouldn't overly emphasize one more than the other. All right, so we will look at that, but it's time for a break right now. So let's take a 15-minute break. We'll start again at 12:48. And we'll continue on with these problems. All right, we're going to start back up again. And so the idea we had was that let's give equal attention not just to the 5 minutes before 15 minutes, but that should get no more priority than the 5 minutes after 15 minutes. So in that case, and let's go to green here. Let's go from 15 to 50 to 20 minutes, 111 gallons. Then the slope here, there's going to be 250 minus 111 over 20 minus 15. And this turns out to be what? 139 over 5? And does anybody know what this turns out to be? Punch that in the calculator. I can punch that out myself.
27.8.
So, oh yeah, and oh, I did this backwards. This is supposed to be 111 minus 250. So the negative 27.8.
Yeah.
Okay. Now, we have ourselves a dilemma. Which one do we pay more attention to? The 5 minutes beforehand or the 5 minutes after, since they're different answers? Or what should we do since we're getting two different answers?
5 minutes beforehand is going to be closer because the rate is constantly slowing.
Does everybody agree with that? The 5 minutes before is going to be closer. I contend that it's yes, it's constantly slowing, so the 5 minutes afterwards is going to tend to be slower than the 5 minutes before, but right at
Probably
15,
averaging the two.
right at 15 is going to be in between those two. That's right. We shouldn't go towards lean towards the faster, which is earlier, more than the slower, which is later. Neither one is really more accurate. So if we average the two, we'll get the best answer yet. So let's let's take those two and average them. Average equals negative 38.8 plus negative 27.8 divided by 2. And what does that give us? Negative, does anybody have that?
Negative 33.3.
Negative 33.3. That's what I would get as my best estimate that I can get. Now, let me point out one other thing. Now let's go to this color. If I skip the 15 to 50 altogether, and I just say, what was the rate of change between 10 minutes and 20 minutes? If I do that, it'll be very interesting to see what happens. Let me shrink this so I can get it in here. And then I'm going to get the slope equals the second one, 111, minus the first one, 444, over 20 minus 10. which is negative 333 over 10, which is negative 33. Whoops. Somehow I got into that. So it's negative 33.3. And you will always get the same answer. If you take these two, the slopes between these 2 points and average them, and then the slopes between these 2 points, and then average both, you'll get the same answer as if you just skip that middle point altogether. It turns out that 250 at 15 minutes or 250 gallons is irrelevant. We don't need to know that number to get the slope, the instantaneous slope around that. All right, now.
I have a question.
Yes. Yes, what's your question?
Sorry, I muted myself again. If we find that slope from 10 minutes to 20 minutes, that slope that we're describing is a straight line, is it not?
That is correct.
But in actuality, the behavior is still a curve that's continually getting less steep as time goes on.
Correct.
Which is why, yeah. So that's why I figured that the slope at that instantaneous time of 15 minutes would be a little bit closer to the 10-minute mark because it hasn't had the time to slow down all the way to the 20. So I'm confused why you wouldn't sort of estimate a little high.
The thing is we know the slope between 10 and 15 minutes is going to give us an overestimate of how fast the water is leaving the tank. Because in the 5 minutes prior to 15 minutes, there was too much water pressure. The 5 minutes afterwards, we know we're going to get an underestimate of how fast the water was leaving the tank because it keeps slowing down in its speed. But as far as to which one is going to be more accurate than the other, I'm not sure. Maybe you lean one side or the other side a little bit, but basically, unless you know more information about the type of curve it is, you really can't lean to one side more than the other.
I see. So the curve could be convex or it could be concave.
That's right. We don't really know a whole lot about that curve. Okay, but we're going to start to look at that now as we go to the next problem. Okay.
Professor?
Yes.
Well, one more comment is that it must be really a linear set of data because if you take 5 minutes and 25, which are even farther apart, you get the exact same average, 33.3 to the decimal.
We're going to look at all this in terms of this graph right now. So
okay.
We're going to, you guys have great anticipation. You're going right towards where we need to look next as we're going to take this data and it says place the dots on the graph below corresponding to the data points. So we're going to make data points for each one of these, place them into this curve, and then in the graph above sketch a smooth curve through all the data points that approximates the actual water flow, and then sketch the secant lines, which is exactly what we've been talking about. And then compute the slope of each of these secant lines and annotate them, etc. All right, so that's where we're at right now. And how you're going to do that on your own computers is totally up to you. Whether you're going to print something out and then write on that, or but I'll work on it here on this, and so let's all put this data in together now. So the first point is 0, 1000, which is way up here. The next data point is 5, almost 700. 5, almost 700. Right about here. 10, 444. We're just rough estimates where these points go. 15, 250. 20, 111. 25, 28. And then at 30 minutes, there's 0. All right. So it asks us now to sketch a smooth curve through all these data points. And I'm going to do my best. There. There's my smooth curve. And then, part 2, it says, of D, sketch the secant lines on the interval 15 to 20. Alright, which from 15 minutes to 20 minutes. Now, these secant lines, I'm going to put these in green. So from 15 to 20, now I want a straight line here. Then draw the secant line, and also from 10 to 15. From 10 to 15, that line's going to go here. Now, you can't quite see it in here, but the curve is such that the left one is more steep and the right one is less steep, like this. Because water is decreasing faster, it's steeper here, it's getting less steep over here. So if I kind of exaggerated the effect, it would be something like this over on the right. Then draw the secant line using a dashed line from the interval 10 to 20. From 10 to 20, the dashed line would be something like this. Okay, and now what we did is we found the slopes. We found this first slope to be like what, negative 38.8, and this next slope to be negative 20 something?
27.8.
27.8, and this one to be in between, negative 33.3. Okay, and then part 3, it says draw the tangent line at the point 15 to 50. Now the tangent line I'm going to put in red. This tangent line just nicks the curve here. Like that. There's the tangent line. Alright, now note that the tangent line in red looks fairly much parallel to the dotted line, more so than it does to either of the other two lines. the other two lines, and so if we kind of came over here, where here is this line between those two, and then this line here, you'd see these would be kind of like parallel lines. And, all right, now, okay. So what we've done is up to number 5. Okay, and number 6 says, hang on. Notice that we didn't use any of the data except for the volumes at 10 minutes, 15 minutes, and 20 minutes. And in fact, the volume at 15 minutes, we didn't really need either. We could have just used the volume at 10 minutes and the volume of water in the tank at 20 minutes. Those two data items, and ignored everything else in the table. Would we get a better estimate of rate at which water is leaving the tank after 15 minutes if we used all of the data? We're only using these 2 points. Wouldn't we get a better estimate if we used all of the data? Anybody have a comment on that? That seems to make sense to me. More data, better answer.
Well, when you originally used all the data, when you looked at it from 0 to 30 minutes and going from 1,000 to 0 gallons, we got a negative 50 gallons per minute. So that wasn't
Yes.
close to.
That's right. That's right. When we included more of the data, we get further from our answer. The best answer we get is when we ignore all the other data. This is one of the strange cases where more data doesn't help. You just want the data that is closest to your place in question. The extra data just is misleading. We can just, this whole table would have been unnecessary. All we needed was those 2 points, and we're going to get our best estimate of how fast the water is leaving the tank from those 2 points, and that's it. All right, in this modern era of big data, where we get so much data, I mean, cars and vehicles and trucks, they're transmitting data all the time so that, truck drivers, they don't have near the amount of breakdowns because so much data is being transmitted from inside their vehicles that they can anticipate when a problem is, something is not quite happening. And the modern motto is the more data, the better. But we're seeing an exception here. All right. So, would we get a better estimate? Nope. Now, let's go to number 7. Describe the difference between a secant line and a tangent line. And then number 8, what does the slope of a secant line represent? And what does the slope of a tangent line represent? All right, so both of these problems, 7 and 8, I want you to, in your groups, come up with the best answer that you can get for number 7, the difference between them, and number 8, what they each represent. And they're going to represent something different. And their difference is going to be important to us. They're very similar, but there's a very important difference. So I'll give you a couple minutes on it.
Professor.
Yes.
From the drawing you made and from other experiences, it seems like the secant lines, there's, at least a couple of them there and potentially ones there, it seemed like they are parallel to the tangent line. Would that be something you could surmise, or very close to the tangent line?
Yeah, and some of them are more parallel to the tangent line than others.
Okay.
That's correct. Yes. Good observation.
If this is symmetrically distributed, like say they're equal from the point of interest, if they are equidistant from that, then you
that's
they
the
should be
observation
parallel
you were
to.
making before. That if I made like this line from here, from here to here, that's approximately parallel to the red line, and from here to here, it's approximately parallel to that as well.
Probably parallel to the tangent as well.
So now that has to do with the symmetry of this particular problem.
Right. Yeah.
Many of the problems we'll look at aren't going to be quite so symmetric. So generally speaking, we just want the data that's closest to the point of interest.
Okay.
Not real far away.
Okay. Yeah. Not something that's necessarily so regular as this. You need to have more.
That's right. This one was incredibly regular and kind of symmetric like that.
Okay. Right. Thanks.
You're welcome. All right. So let me ask group 6. What's the difference between a secant line and a tangent line?
Sorry, my mic was off.
Okay.
So basically, the secant line gives you the average rate of change between two slopes, whereas the tangent line gives you the instantaneous slope.
Very good. And we're going to say the secant line here gives us the average rate of change, and the tangent line gives us an instantaneous rate of change. Now they're both slopes, but they're slopes of, now the secant line, you know how many points? 2. You have to have 2 points. Tangent line, you have to have how many points? 1 point. You can get the tangent line at t equal 15. That's what we're looking for. With just that 1 point. The others are secant lines, and the thing is tangent lines are hard to get. Secant lines are easy to get. You just got the 2 points and you use the slope formula. So what we do is we use secant lines to help us get tangent lines. Tangent lines, hard, but that's our goal. Remember when I was describing the whole purpose of this was way back here, we're trying to get an instantaneous slope. Like, when were you going exactly the fastest? Or what was the exact speed after 2 hours? And, even though 1 billionth of a second later it's going to be a different speed, what was the exact speed when t was equal to exactly 2? Well, that's a tangent line. And we use secant lines to help us get to tangent lines, because secant lines are easy to do. You get 2 points, you just subtract the y's, and then subtract the x's divided off.
Professor, I have a question.
Mm-hmm.
So is this basically figuring out non-right triangles for any line? So because it looks like any line we make is going to be non-right triangles. So you're finding out the angles for each point with the point of the triangle, which is the opposite of the hypotenuse, is the tangent line.
Okay. Generally speaking, we're going to be departing from right triangles on this. But if you did insert the right triangle perspective into this, the tangent function from sine, cosine, tangent, turns out that the tangent is the opposite over the adjacent, which is the same as the rise over the run. And so the tangent of an angle, if it was in standard position, turns out to be the same as the slope. But that's as far as we're going to get as relating this to right triangles. Generally speaking, we're going to depart from that world of trigonometry and right triangles, except for certain times that we'll go back to there. So I'm glad you pointed that out, Kylie. But it's generally speaking, we're not going to look at this in terms of right triangles. Neil, you also had something?
Oh, no, that's okay. Thanks.
Okay.
I'm good.
All right. All right. Any questions on this?
I was just thinking from last semester about the non-right triangle formulas that you told us.
Like the law of sines and law of cosines?
Yeah.
Uh-huh.
Does that equate to what we're doing?
Not really, because they would still have to do with triangles. And we aren't going to put a triangle into this situation. It's more like looking at these kind of graphs, this kind of the black curve, and saying, what's the instantaneous slope here? What's the instantaneous slope here? Not really in terms of triangles. Yeah, I think it's just a different context. Anything else?
I have a question.
Yes.
So you can do that for like any kind of graph, even if it was even if it was a parabola.
Yes. We are going to wind up looking at situations like that. Basic parabola. And we're going to say, what's the tangent line, slope of the tangent line at all these different points of the parabola.
And so when we find something like that, then we would just be finding the average of whatever the slope would be.
That's how we're going to start looking at it. This is only the beginning of this. We're eventually going to get to where we're going to get we're going to, believe it or not, and this is pretty bizarre, but let me just kind of give you a glimpse of where we're going. If you have a parabola, we might start by asking, we'll be doing this in a little while, we'll be saying, when x is 1, so here's x is 1, we'll be saying, what's the exact slope of the tangent line when x is 1, when it just nicks the curve there? And we'll be able to figure that out exactly. Not just approximately, but we'll get the exact slope of this parabola when x is 1. Now it looks like kind of like a slope of maybe 1 or 2 or something like this. It's definitely a positive slope. It's going uphill as you move to the right. All right. Later on, we'll get to something that will be so powerful that it will be a really compact equation that will tell us the slope at every single point on this parabola. That you'd be able to ask me, what's the slope of a parabola when x is equal to 3? And I'll be able to instantly tell you the answer because the computations will go so incredibly quick. We'll eventually get some incredibly powerful shortcuts. But what's really important, though, is to remember your foundation of what we're really after, which is the instantaneous slope. And the instantaneous slope at the beginning, how we approach it is we're trying to find the slope of a tangent line. How do we find the slope of a tangent line? Well, the only thing that we can really do is look at secant lines at first. And we need 2 points to find the slope. And then But we want those 2 points as close as possible to this point right over here. All right. Anything else? Any other questions? All right. I want to shift back now to some more of this practice quiz. And do problem number 1, the sine of 2 pi over 3, and then go ahead to problem number 2 as well. Do both of those. I'll give you a minute. Okay, 30 seconds more. Okay, number 1. I might do this one by first drawing a little unit circle. And pi over 3 is right here, 1/3 of the way over to pi. And 2 pi over 3 is up here, 2/3 of the way over to pi. So my angle is right up here. And the sine is the height of that. And of my 3 values, 1/2, square root of 2 over 2, or square root of 3 over 2. This one only occurs when they're equal, at 45-degree angles, at multiples of 45-degree angles. These two, this one, its decimal equivalent is 0.5, this decimal equivalent is 0.707, this decimal equivalent is about 0.86. So this one is bigger than this one. So the height is higher than the distance over. So its height is square root of 3 over 2. This one is asking the inverse cosine of -1/2. It's asking what is the angle when you take its cosine. Now the cosine gives you the x-coordinate. What is the angle whose cosine is this? So it's got to be directly above that. Okay, so that angle over there is just pi over 6 units up from there, so it's 5 pi over 6. All right, now the inverse cosine has to do with its 2 quadrants that it's restricted to, are quadrants 1 and quadrants 2. If it had been the inverse sine of -1/2,
Wouldn't that be 2 pi over 3?
for -1/2, oh, you're right.
Yeah, I agree.
That is correct. Let me erase that. Alright. Because we're, oh, you know what, my -1/2, I put it too far over. I should have been more like over here. So then it should have been up here. because it's more like this. So this is going to be 2 pi over 3. And it didn't specify whether it wanted in radians or degrees. Our default is always radians. Thank you. Now if we'd been inverse sine of negative 1/2, that would have been when I make really small marks, it thinks I'm doing something else. So it would have been over here. So what's the angle that's going to do that? That is negative pi over 6 for this one. And the inverse sine function is in quadrants 4 and 1 are the only two quadrants it's defined in. And when you're using a quadrant 4 angle, you have to give it as a negative angle. All right, so let me have you go to number 3. And these problems, I have to cut and paste from different portions, and that's why this doesn't look right next to this one. So there's the problem, and there's the restriction on the x. If x is between 0 and 2 pi, solve that equation. Now a hint, you should be getting more than one answer for this. Okay, let me have you stop. So here we are going to bring the 1 to the other side. So I get square root of 2 sine x equals 1. Divide by square root of 2. Sine x is 1 over square root of 2. If I rationalize the denominator by multiplying top and bottom by square root of 2, it's the same as sine x is square root of 2 over 2. That seems familiar to us. What's the angle who, when I take its sine, I get square root of 2 over 2? Well, I draw my unit circle. It's this angle right here. So, at first glance, you'd say x is pi over 4. But that's not the only answer. X can be any angle within one complete revolution. What's another angle that will also give you the sine being square root over 2?
5 pi over 4.
It's pi over 4 is
Pi over 4 is.
and then there's another one.
And there's another one. 5 pi over 4.
Now if we went 5 pi over 4, that would be here.
That would be here.
3 pi over 4.
Pi over 4. Yeah.
And then the sign would be negative. We'd be down in the right. So it'd be, actually we want to be up here. There's the other angle. And then that's 3.
Correct, 3 pi over 4.
Both of them have the same height right here, which is square root of 2 over 2. Okay, so that's how we get our two answers when we solve trig equations. All right, and now we've gone over everything. I want to point out that in 2.1 in the homework problems, they're going to ask you for, it'll be a rather similar situation, but if this is time and this is a distance, then the velocity is going to be, the slope will represent a velocity. So many of the homework problems are time here, distance here, and then instead of asking for a slope, they can ask for the velocity. All right, now, some general things. What's coming up is, let's go to this. All right. If you look at our schedule, you'll see that we have a test coming up on Tuesday. And today it says students start working on the take-home portion of exam number 1. And so let me go into the modules. And, let me get into student view first. Okay, so now in the modules. And today you have the 2.1 textbook homework. You also have this tangent lines and secant lines worksheet. And if you click on this, you see here was the worksheet that we did in class today, and here is the homework related to that. So there are some problems. So if I click on one of these, it's student homework problems. All right. So, and there are selected answers for these as well. And you may find, since these are more similar, you may find you have an easier time with this. You might want to do this first and then do the 2.1 problems. All right. And let's get back to here. So after that, you see the take-home portion of exam 1. And if we click on this, you see there's as a Microsoft Word document and the same thing as a PDF file. And this is due Monday at 11:30 a.m. So on Monday, before we have class, upload your answers for the take-home portion of exam 1. Now this does include the 2.1 material that we just covered today. Those kind of problems are in this take-home as well. So you want to do probably you want to do the take-home, do the 2.1 first, and then work on these problems and get them uploaded. On Tuesday, all we're gonna do in class on Tuesday is take exam 1. And so if we go to exam 1, which is the very next module, it will just tell you it's locked. It becomes unlocked on Tuesday at 11:30 a.m. And then you can download it, work on it, and then you upload your answers by 1:45 p.m. So same time, same length of class, but all we're doing is you do the exam 1. Now, what I want you to do in between Monday and Tuesday when we have the exam is I'm going to be asking you to get together with the members of your group and go over your take-home answers to make sure that everybody really understands and is comfortable with the answers that they're getting. And I want you, when you get together, this should be somewhere between Monday and Tuesday. So you've turned it in, and then after you get together and refine your answers, you can re-upload and make sure that your answers are super correct. So I'm going to check to make sure that you've uploaded this at the right amount of time, at the right time, Monday at 11:30, but I'm not going to check it for correctness then. That won't happen until Tuesday, so that you have a chance with your group members to go over, make sure you're really comfortable with all of your answers. And in fact, I will also post correct answers for the take-home portion. I'll post those sometime Monday afternoon, because once in a while it's even happened that entire groups have thought, this is the correct answer for this problem, but they were all wrong. So you can double check against mine. So I'm really kind of giving you an easy 20 points on this exam. There's no reason you should get any of these wrong on the take-home portion. And then the other 80 points you'll be taking individually. On Tuesday, again, you're on your honor to take the exam under the same conditions that you would be taking it were we at the community college, which means you cannot use the internet to look up answers. You can only use a non-graphing calculator. You want a nice scientific calculator, but they're like 20 bucks or something like this, and use that for the exam. Any questions about how the take-home and the in-class exam will be working? Everything clear? Okay, we've got just a few more minutes. Questions on homework. Let me go over here. You can type in if you have any questions, or you can tell me verbally any leftover questions on homework. Okay. Number 75, and was that on the 1.4, Alondra?
Yes, 1.4.
1.475. Evaluate the inverse tangent of square root of 3. Alright, so let me just take it down to the bottom. Alright, so I'm looking for an angle theta. Now, for instance, if I put a theta equals this, I could take the tangent of both sides and turn it into this. Tangent of theta is equal to the square root of 3. Now, the tangent is the same as the sine over the cosine. Now, to get square root of 3, think of square root of 3 over 1. If I got the sine to be square root of 3 over 2, and I got the cosine to be 1/2, watch what would happen. You'd invert the bottom fraction, and we would get exactly what we want right here. And so these two 2's wind up canceling each other out. So what's the angle whose sine is square root of 3 over 2 and whose cosine is 1/2 on the unit circle? That would be the sine is the bigger one. It's this one up here. So that's going to be pi over 3. Does that answer your question, Alondra?
Yes. And then someone asked on the if how are we going to submit the final homework for this week?
The final homework for like 1.4?
Yeah, like oh well, 1.1, 1.2.
Through all those? Okay.
Yeah.
Whatever you have left in there. So when you're in the homework submission, so if you're in the modules and you're at the 1.1 homework, when you submit your assignment, you get to upload a file. Now, if you have modified it and changed your answers, is there a way to remove what you did or do you just submit another document on top of that?
Yeah, what it says is just resubmit if you've already submitted that button.
And
Wording
does it
changes.
replace the other one then with that?
I mean, I don't know what happens on your
Yes,
end.
it does.
It just does
replaces.
replace it? Okay.
Yes.
All right. And so you just submit again and it'll replace it, and then that's the one I'll see. So the schedule says that today's Thursday. What's due today is 1.1 and 1.2. And then also I'll be spot checking the 1.4. But 1.1 and 1.2, by midnight tonight, you got to have your final versions of those in. So then, tomorrow, starting in the morning, I can be looking at those in detail and give you the complete grade for those.
So the final version of 1.4 is not due tonight?
Today, all that's due is 1.1 and 1.2. The spot check for 1.4 is due today. Okay. And,
okay, great.
The 1.1 and 1.2, if I look at it and everything that I see is correct, you're going to get 100%, but only if you also had, uploaded the spot check within the correct time. If you had not, you'll only get 6 out of the 10 points. But if you had uploaded the spot check, by that time you'll be getting then the full 100% if you had everything correct.
Professor, I started the class on Tuesday, and so
Yes.
wasn't able to get the spot check for 1.1, the very first assignment. But I will be submitting that by the end of today. Will that still affect my credit?
I won't take any points off for that because that was out of your control. So you get 100% for that.
And then the other question I had was on the homework for 1.2, and we went over it. For some of the transformations of the functions, in my equations, I didn't do some of the factoring that you had asked for, but when I gave the explanation of what transformations happened, they matched your answers. So do I need to go redo that, or can I leave it as is?
You can leave it as is. There are multiple ways to get to answers. You don't have to do it my way. That is
okay.
Correct. Mm-hmm. Anything else? Any other questions? All right, so there's a lot to do over the weekend. You've got to get the take-home exam done and completed before 11:30 on Monday, as well as the 1.2 and the worksheet homework. As well as 2.1 and the worksheet homework for the worksheet that we did today. It's a good thing that all that happens over the weekend. And I will see you all then on Monday. When will our homework be graded. I'll be grading over the weekend, so probably by, by Monday morning, you'll have a grade. Probably late Sunday. Oh, and I'll stop the recording.